In this video, we're going to focus on the refraction of light. This is a property of light that causes it to bend when it passes from one medium into another. And this picture really shows the refraction of light. You can see this glass rod is bent at the interface between air and water. So here we have the interface between air and water, and this vertical dashed line that I'm drawing represents the normal line. The normal line is perpendicular to the interface between air and water. It's at a 90-degree angle. Now, when a light ray strikes the point of incidence, three things could happen. The light ray can reflect at the boundary, it can refract, or it could be absorbed by the material. This is known as the incident ray. This is the reflected ray. And the one on the bottom is the refracted ray. The angle of incidence is the angle between the incident ray and the normal line. So let's say that's 45 degrees. According to the law of reflection, the angle of incidence is the same as the angle of refraction. So these two angles must be equal to each other. Now my drawing is not precise, so it may not look like they're the same, but they should be the same. Now this angle here is known as the refracted angle. And in order for us to calculate that, we need to use something called Snell's law, also known as the law of refraction. And it's n1 times sine theta 1, which is equal to n2 times sine theta 2. So that's Snell's law. It can help us to calculate the angle of refraction or the index of refraction. The index of refraction for air is approximately 1. For a pure vacuum where there's no molecules in the air, it's exactly 1. The index of refraction for water is 1.33. So with this information, we can calculate the angle of refraction. So n1 we're going to say is 1 and n2 is going to be 1.33. So it's 1 times sine 45, and that's equal to 1.33 times sine theta 2. Sine 45, that's equal to the square root of 2 divided by 2, which as a decimal is 0.7071. If we divide that by 1.33, we'll get that 0.53166 is equal to sine of the second angle. Now, in order to calculate that angle, we need to use the arc sine or the inverse sine function. And that will give us theta 2, which is the angle of refraction. So if you type in an arc sine 0.53166, it'll give you an angle of 32.1 degrees. So that is the angle of refraction. So notice that as the incident ray moves from a material with a low index of refraction to a material with a higher index of refraction, the ray bends closer to the normal line. The angle decreased from 45 to 32.1. Now the reverse is true. If the incident ray traveled from a material with a high index of refraction to a material with a low index of refraction, the angle is going to increase. And so it's going to bend away from the normal line as opposed to toward the normal line. Now, another interesting fact that you want to know for this topic is the speed of light. The speed of light is not always 3 times 10 to the 8 meters per second. In fact, it changes based on the material that it is traveling in. This is the speed of light in a vacuum. The speed at which light moves depends on the material it's moving in. And here's how you can calculate the speed. The speed is equal to the speed of light divided by the index of refraction. So the speed of light in air is going to be 3 times 10 to the 8 meters per second divided by 1, which is 3 times 10 to the 8 meters per second. Now what about in water? How fast does light travel in water? Well, we can calculate that using the same formula. So it's going to be V is equal to C over N. So C is not going to change. That's going to be 3 times 10 to the 8 meters per second. If we divide it by 1.33, which is the index of refraction of water, we can get the speed of light in water. And so in water, light travels at 2.256 times 10 to the 8 meters per second. So notice the relationship between the speed of light and the index of refraction. When light travels in a material with a high index of refraction, the speed decreases. So diamond, for example, has a very high index of refraction. If my memory hasn't failed me, I believe it's around 2.4. So light travels very slowly in diamond, but it travels a lot faster in water or air compared to diamond. So far, we've considered the example where light travels from a material with a low index of refraction to a material with a high index of refraction. And we saw that the light bent closer to the normal line. Now let's consider the other situation. Let's say we have glass on the bottom, air on top. The index of refraction for glass is 1.5. There's different types of glass out there, but for the most part, it's close to 1.5. So this is going to be the incident ray. And this time, the refracted ray is going to move away from the normal line. Let me make this angle smaller. So I'm going to choose an angle of 40 degrees. So that is the angle of incidence. Now let's calculate the refracted angle. So it's N1 sine theta 1, which is equal to N2 sine theta 2. So N1, we're going to say that's for glass. That's 1.5 times sine of 40 degrees. That's equal to N2, the index of refraction for air, times sine theta 2, or theta r for the angle of refraction. So 1.5 times sine 40 is 0.96418. So the refracted angle is going to equal arc sine of 0.96418. So the refracted angle is 74.6 degrees. So when light moves from a high, let me say that again. When light moves from a material with a high index of refraction to a material with a low index of refraction, the light ray bends away from the normal line. Now there's something interesting that's about to happen here. Notice what's going to happen if we increase the angle of incidence. If we increase it, the ray is going to bend even further. At some point, the ray will travel in between the interface of air and glass. And if we increase that angle even further, something called total internal reflection will occur, where all of the light rays will reflect and none of it will be refracted. But before total internal reflection occurs, there's something called the critical angle, which the angle of refraction is equal to 90 degrees. That's when the light ray is between the two boundaries, as represented by the ray in red here. Let's calculate that critical angle. So once again, we could use Snell's law. So N1 is going to be 1.5 times sine. The incident angle is the critical angle. N2 is 1. The incident angle is the critical angle when the refracted angle is equal to 90 degrees. So sine 90 is 1. So we have 1 divided by 1.5. And that's equal to 0.6 repeating. So the critical angle is going to equal arc sine 0.6 repeating, or 2 over 3. So in this example, the critical angle is 41.8 degrees. if you choose an angle that's greater than this number, total internal reflection will occur. But if you make the incident angle equal to the critical angle, then the refracted ray will travel along the boundary between air and glass, which is an interesting phenomenon to see. So that's basically it for this video. Hopefully it improved your understanding of the refraction of light and how to calculate the incident angle or the critical angle or even the refracted angle. So keep in mind, the incident angle could be anything between 0 and 90. The critical angle is a specific incident angle when the refracted angle is 90. So even though the incident angle can take on many values, the critical angle can only take on one value. It is a specific incident angle where the refracted angle is 90. Just want to clarify that in case there was some confusion.